times 5 factorial divided by 4 factorial, which is nothing but 5. But anyway, no matter how complicated it looks, ultimately there will be a positive integer that will be the answer. Finally, for D, we have to consider those words or those arrangements. I should not say words because these are not meaningful words. These are just juxtaposition of letters. If you put one after another, they don't form any meaningful word except that first one, independence, or they may form some meaningful word if you just interchange some letters, anagrams you call them. But here, however, they start with I and end with P. So just like that one, this one, which starts with P, this one starts with I and ends with P. Now instead of having only the first place fixed, we have both the first and the last place fixed. Last place is fixed. So now here we have 10 possible places for variation, and accordingly we have 10 different characters remaining for us. I and P have been taken. Okay, so for the remaining 10 characters, the repetitions have to be accounted for. Now there again, n is appearing 3 times, so 3 factorial, we divide by 3 factorial. D is appearing 2 times and E is appearing 4 times. So this is the answer for part D, and that completes the solution. You can use calculators to find these values, but knowing the method is more important. Right. Okay, now we come to combinations. So permutations are, but before introducing combinations, I think I can discuss one more thing, which I mentioned at some point. Circular permutation. Okay. So let us take an example and try to understand this. Now instead of arranging the objects, we are again in a situation where we have distinct objects, right? And instead of arranging the objects along a line or along an open curve, we arrange the objects along a closed curve. The shape of the curve, of course, does not matter. You can think of it as a circle. So, say we have 3 objects, 1, 2 and 3. Since they are distinct, I can create a set out of them. Now they have been arranged along a circle. The question is, in how many ways can this be done? If you think it is still 3 factorial, you would be wrong, unfortunately. Why is that so? You see, these are called cyclic permutations. simply because the objects are appearing as a cycle in a cyclic pattern. Now, if I try to think of this arrangement, I can think of it either in clockwise direction or anti-clockwise direction from this point of view, okay, looking from above. Now, if I think of it in clockwise direction, after 1 I get 2, after 2 I am getting 3, after 3 I am getting 1. 1, 2, 3, 1, 2, 3, 1, 2, 3. Or if I start from 3, 3, 1, 2, you see the thing, 1, 2, 3, 2, 3, 1, 3, 1, 2. Okay, these arrangements, if I had a linear pattern like this, like 1, 2, 3, if I had a linear pattern like this, these arrangements are of course different permutations. However, when I have a cyclic pattern like this, where we start from one point and then come back to that point along any curve, closed curve, then these patterns actually create the same cyclic permutation. So instead of having 3 distinct permutations, linear permutation, if I say so, it's not a standard term, I have one cyclic permutation. However, for this one, the thing is slightly different. Why this cyclic permutation is different from this one? It's because if I go clockwise, after 1 I get 3, and then I get 2, and then I get 1. So 1, 3, 2, 3, 2, 1, or 2, 1, 3. Have I written it correctly? Yeah, after 2 I have 1 and 3. So these permutations give rise to this cyclic permutation, these 3 linear permutations. When we go to that subject called group theory, there we will see that these things actually appear as cycles or something like this. But more about that later. So the question is, what is the number? Here we see that the number is 2. It's not 6. These 3 linear permutations have collapsed and they have given us this single cyclic permutation. These 3 linear permutations have collapsed and given us this single cyclic permutation, and they are different. Okay, provided we first of all fix the sense of the rotation either clockwise or both counterclockwise. Then we get different cyclic permutations, but we are getting only 2. So what is happening here? You see, when we consider linear permutation, there is a first object, provided we are deciding to go from this side to that side. You see, we are not switching the order. You can get my point if I write like this. Let me elaborate a bit more. What I am trying to say here is this. Suppose I have 4 objects, 1, 2, 3, 4. Okay? And I write 4, 2, 3, 1. These 2 permutations are of course different. Why? Because if we fix a direction, if we decide to read from left to right, then these objects are not matching. So they are different. Here also we have fixed a direction and then we have moved. But instead of, unlike this case where we have a first element, here there is no such reference point from where we can start. That point has to be fixed by us. If we fix 1, then the 3 and 2 can among themselves be permuted. Do you see my point? I can break this chain and I can write 1 here. I had 3 here and 2 here. Instead of having this cyclic pattern, if I break this bonds, then I have 1, 3, 2, deciding to go counterclockwise or in this way. Now this is a cyclic permutation. Since I don't have the bond, now if I write 2 here and 1 here instead of these 2, I will have a different thing, 2, 3, 1. But am I saying the correct thing? Yeah, 2, 3, 1. Now, but if I had this bond, then I would have had 1, 3, 2, 1, right? But if I write 2, 3, 1, then I again have 1, 2, 3, 1. So if I don't fix a reference point, then I cannot start counting. Okay, for me to be able to start counting, I have to first of all fix a reference point. In linear permutation, that point is either this side or it starts from this side. Okay, that is already fixed. We are not starting from here. So that's why we first of all fix one point and then count the number of ways we can arrange the remaining points around that point. Okay, so that's why we are getting 2, and that 2 is nothing but 3 minus 1 factorial. From the 3 elements, we have fixed one element, reducing the number of elements by 1. So now we have 2 elements for arrangement. 1 is fixed. So that's why we have 2 factorial, and 2 factorial is nothing but 2. So if we have n distinct objects, then the number of permutations of these objects around a circle is not n factorial but n minus 1 factorial. Further, if you are not distinguishing between counterclockwise and clockwise rotation, these two are also the same. So in that case, if that is also given, then this is further reduced to half of that value, which in our case will be only 1, because 2 by 2 is 1. So that is circular permutations. I am not going to discuss some very complicated things about this. At one point, I think we will deal with some pretty hard problems on permutation. There we will see these things. Okay, so let us now go to combinations. Let me start from here. At once, at first glance, this may have gone over your head, but you think about it, okay? You think and try to see what is happening. You may take a bigger example which involves 4 objects, and you may try to see what is happening and actually how many cyclic permutations we get. There also we won't get 24. There we will get 4 minus 1 factorial. So there we are getting 3 factorial, or only 6 permutations if 4 objects are to be arranged around a cycle or circle. Anyway, so let us start Just like how we started permutations, let us start with cat. Okay, this word cat. Now combinations. Combinations involve forming groups of some objects. If some objects are given to us, a collection of objects, and we have to form groups by taking some of them from those given objects, and where we are not concerned about the order of the objects in which they are appearing, there are no arrangements, just some groups, then we are getting combinations. So let us first of all write down the permutations of this that we already had. Okay, CAT, CT, we already know what this is. Or, no, not all the objects I'm going to take. Out of these three letters, am I being vague? What I'm trying to do is that, again, we have a word and we consider the letters, and now we want to form groups. But first of all, since we have seen so many things about permutations, we want to take that route, and we go to combinations using permutations, although it should be the other way around. You will understand what I mean soon enough. Okay, so we have three letters. Out of these three letters, we are going to choose two and form group. I can choose C and A, or I can choose C and T, or I can choose A and T. Okay, so these three groups are possible where each group has two objects. Now I need to know this number 3. This is the number of combinations of three objects when two are taken at a time. And just like permutations of n objects when r are taken at a time has a symbol NPR. This one also has a symbol NCR. P stands for permutation, C stands for combinations. Okay, now how are we getting this number 3? That we have to understand, just like what we did in case of permutations. So we said that we first of all write all the permutations and then see what is happening. So clearly we have these permutations. Okay. Now what is happening actually? When we form a group, we are not concerned about the order of the objects. That's why we have written a set of those objects, because in set we are not concerned about order. But in permutation, we are of course concerned about order. CA and AC are different permutations, but they give me only one combination, which consists of these objects C and A. Similarly, CT and AT. Now, so you look at it like this. Suppose from C, A and T, I have chosen C and A. Okay? And I have formed the permutations by permuting those objects C and A. So these are the permutations of objects taken from this set, which is one combination. These are the permutations taken from this set, and these are the ones with objects taken from this set. So the process goes like this. If I had to count 3p2, what is the physical process? I mean, without that does not involve the formula. I am to write permutations of three objects when two are taken at a time. So what I first do, I first take two objects. I choose two objects in how many ways possible. And then individually I permute those objects. Okay, that gives me the total number of permutations. So the first step gives me the combinations, and then the next step gives me the permutations. The first step is choosing the objects, and the second step is arranging the chosen objects. So that means the 3p2 that I am getting is actually the number of combinations, which in this case is 3, in symbol, that is 3c2, which we don't know. Okay, this is what we want to find. In this case it is 3, but in general we don't know. Times, for each such choice of objects, we are permuting them. Now two objects can be permuted in how many ways? Because they are distinct. Oh, the objects are distinct. Okay, 2 factorial ways. For each, I mean, there are two objects, so they can be permuted among themselves in 2 factorial ways. Now this is a variable for me, or this is unknown. This 3c2 is unknown. I don't know any formula for this. For 3c2, in this case I have 3. But for 3p2 I already have a formula. So this is known. And this of course is known. So I see that 3c2 is nothing but 3p2 divided by 2 factorial. Okay. Now let us take a second example that will make matters even more clear. Okay, now we have, say, naturally the next word that we considered back then, rows. Now here, out of okay, I am going to again, for the sake of understanding, I am going to again write all the permutations. Okay, bear with me for some time. Okay, but instead of writing the permutations with all the objects involved, I choose to take only 3 objects and write the permutation. So here I am counting 4p3. Out of 4 distinct objects, I am choosing 3 and writing the permutations. Right, so EOS, ESO, SOE, SEO, then RSE, RES, ERS, ESR, SRE, SER. So here OSE, RSE, then ROE, REO, EOR, ERO, OREOER, and finally ROS, RSO, SOR, SRO, OSR, ORS. So these are the 24 permutations of 4 distinct objects when we take, out of them when we take 3 at a time. 4p3 is also 24, which we can find from the formula. But now the question is, if instead of writing these permutations just by looking at these words like this process also involves 2 steps, just like this one. In the first step, we choose the letters that we want to permute. So here we have chosen O, S and E. Here we have chosen R, S and E. We have chosen to remove O. Here we have removed S and chosen R, O and E. And finally, we are not considering E here. We have chosen R, O and S. So this is the first step. In the first step, out of 4 objects, we have chosen 3. So that gives me the combinations. But if we want to write the permutations, then those chosen objects have to be arranged. So this is the second step. This is the first step. So you can see that the second step in this case gives me 24 permutations. So here also 4p3 is the total number of permutations, but 4c3 is the unknown, which is this. And from this actual example, we see that it is 4. Okay. Now, this. So now, having chosen the combinations, then the elements of each group are permuted among themselves. And that number is 3 factorial. Why? Because there are, in each case, there are 3 elements. So that number is giving me the total number of permutations. Here again, this is known and this is unknown. So the unknown can be found out by solving this equation for the unknown. 4c3 is 4p3 divided by 3 factorial. So now you can see easily what the general case will be. If you have n distinct objects, let me now write the general case. If we have n distinct objects, suppose we have n distinct objects where n is a positive integer and r lies between 0 and n. Okay, then the number of combinations of these n objects taking r at a time Okay, I should not have written 0 here in the beginning. Let me write 1. Okay, to make matters simple, I will add 0 separately afterwards. So this number is denoted by NCR, and this is nothing but the number of permutations of n objects when we take r at a time divided by the number of arranging r objects among themselves. You can, looking at the process, this becomes clear. Now for NPR, we have a formula. N factorial divided by n minus r factorial. This is divided by r factorial. And this equals n factorial divided by n minus r factorial times r factorial. So this gives you a formula for the number of combinations. Okay, and this is the derivation of the formula. Using this formula, we can find the number of combinations. So let us now use this formula and see some Example means, yeah, I can take example. Say we have 5 different objects, okay, 5 distinct objects, and I want to find the number of combinations or number of groups of 3 objects that I can form from among 5 objects. So that number will be, according to the formula, 5 factorial divided by 5 minus 3 factorial times 3 factorial. So this becomes 5 factorial divided by 2 factorial times 3 factorial. And what is this? 5 times 4 times 3 factorial. 2 times 2 factorial is 2, 3 factorial. So these two cancel out. So I have 10. So 10 sets can be formed using 3 elements from out of 5 elements. Okay, 5 distinct elements. Now here you can see that R is restricted to be a positive integer. But if I consider the special situation where I do not choose any object, from out of n objects, if I suppose n distinct objects are given to me, I decide to not choose anything. In how many ways can that be done? Only one way, namely that I do not choose anything. So in that case, the number of combinations should be 1. Now, does the same formula work for this particular situation? If R is equal to 0, the left hand side, from common sense, I can say that this is 1, because I can only choose no objects from out of n objects in only one way, namely not choosing them. What is the right hand side? N factorial divided by n minus 0 factorial times 0 factorial. So separately, the right hand side is n factorial divided by n minus 0 is n times 0 factorial is 1. So these two cancel out and they give me 1. So we see that in this special case, when R is equal to 0, the same formula works. The left hand side is the number of permutations of n objects when we don't take anything at all, and the right hand side is a mathematical expression, and they, in this case also, they are equal. So I can write 0 here. Okay. Now these numbers, this NCR, these numbers, instead of denoting them like this, there is another notation. You write n over r and enclose them within round brackets. This is also, they mean the same thing. This and this are one and the same. Okay, they are written in a particle fashion, and these are called, these numbers have a name. These are called binomial coefficients. Why are they called binomial coefficients? We will come to that later when we study the binomial theorem, where these numbers occur as coefficients of some things. Okay. Now these binomial coefficients, aside from their application in counting the number of combinations, have some intrinsic properties. Okay. So there are many properties involving them, but 2 main properties are like this. N and R, of course, n is a positive integer, and R, these things are understood, okay? When we write NCR, these inequalities or these restrictions are understood. The first property is NCR equal to NCN minus R, and it's not very difficult to show. Let us start with the right hand side and see what it gives us. NC n minus r. Now you have to be very careful when you change something in a mathematical expression. Here I have written n minus r. What about n minus r? You see, this, if you think of this n minus r as something, say r prime, okay, nc r prime, then the r prime also has to satisfy this. Otherwise this formula will be meaningless. Otherwise I won't be able to put n minus r here. So let us see what n minus r is. You see, r is, what are these inequalities saying? R is greater than or equal to 0. If I multiply r by minus 1, then the inequality changes. Minus r is less than or equal to 0. Add n on both sides, you get n minus r is less than or equal to n. So n minus r does satisfy one half of these inequalities. What is the other half? Since n is greater than or equal to r, if I subtract r from both sides, I get n minus r is greater than or equal to 0. So this is also greater than or equal to 0. That means there is no mistake in putting n minus r here for these values of r. Okay, these things have to be kept in mind. If you see something like this, it does not make sense. 5c7, this is meaningless. Okay, this symbol has no meaning. The one that appears below as a suffix, it should not exceed the one that is appearing above.